All right. Hopefully this is on and you can hear me. Okay. So I'll talk about Koopman operator theory-based machine learning of dynamical systems. I will describe a little bit what the field looks like here, because Median asked me to do so. Just a little bit of an overview, but I'll also go into a few things that we have been doing recently with my group and my collaborators on development of these kinds of methods. You might or might not be aware of this approach, so I will go through a sequence of settings and ideas to kind of describe it. So I will talk, here's my plan. I'll talk about the Koopman operator, history and modern use, objectives in learning of dynamical systems, somewhat from the perspective of Koopman operator theory, but I do want to convey the idea that you can do a lot of the objectives in this particular framework, whichever way you execute that framework. And then I'll talk specifically about a new concept. I did talk about it a couple of years ago here in the same symposium, just online because it was COVID, this concept of representations that I'd like to kind of frame the whole approach within. I'll speak about how do we do numerical analysis, some of the aspects of that, talk about the robustness to noise and Koopman theory with uncertainty. That's a recent work that I hope is going to appear on arXiv one of these days. A little bit on control. There is quite a number of different uses in control theory by now of this. And then some discussion of place of Koopman operator theory in AI, but I'll try to do this through a variety of examples. Koopman operator on neural networks for algorithms and in soft robotics, and then I'll conclude. So that's the plan for today. So let me briefly review conceptually where we stand. Learning is, as presented here, is going to be based on. Okay, with that little interruption, let's continue. So my goal here is specifically to connect the Koopman operator theory to learning, and even actually a little bit more broadly to quote-unquote AI. I'll try and define what it means in my view as we go, but you will see that the approach turns the concept on its head a little bit. I think for those of you that are working in Koopman operator theory, typically start, and that's what von Neumann and Koopman did, from a dynamical system, and then you say, well, there is a linear operator associated with it. As you're going to see, I'm going to invert that. And that at least proves useful to me conceptually. I hope it's going to prove useful to you. Just a reminder, because I said I'm going to talk just a little bit about history. This was classically used to study measure preserving systems way back in the 20th century, just as quantum mechanics got started. For dissipative systems, there is a whole literature in mathematics under the nomenclature of composition operator, because Koopman operator is composition operator, and it's a very interesting literature. It approaches it a little bit different than dynamical systems people in general. It starts from an operator theory perspective, but it's well worth knowing within this context. So the elevator pitch is that if one looks at this operator that I'm going to define, then if you find the spectral objects associated with it, and I'll define that, then that helps with analysis of state space geometry and enables model reduction in control. As I said, that's an elevator pitch, but I'm hopefully going to convince you of the truth of that. Skipping to modern day, today we're doing a lot of work in adjusting, adapting this kind of a theory in learning and artificial intelligence. Quite a bit of that, and I'll show you some towards the end. And a particular aspect that's interesting, because Koopman operator is in essence a time shift operator, and it knows about time somehow, right? Its invariances are time invariances. So it knows, its characters are exponential functions. It knows about time somehow. It's capable of learning in the way that neural networks are struggling to do, in a sense, because it adapts and figures out the long-range projections pretty quickly. So there is a capability of learning with minimal supervision and learning very quickly. Hopefully, I'll get to the last slide and show you quite a nice example of that from our lab. It's more and more used in control. Learning from small number of samples is something that it's particularly good at. The way one should think about this is one doesn't need a neural network to tell us that a function is a sine function, right? A small number of samples with a little bit of Fourier analysis is going to do. And for those of you that are deeply steeped into this, of course, fast Fourier transform is an example of a neural network. I don't know if you've seen the really nice write-up in Science News on this, but it was kind of interesting. The original algorithm was actually an NN, or it can be represented like that. Okay, what are the issues that we are facing today? You will see that we somehow need to select the function space for closure. I'm going to try to answer that using representation theory and give you several examples of which choosing the function space is appropriate. Robustness to noise. Because of it being particularly suited to dynamical processes, you made one little correction to make it work in the stochastic domain. But we are doing a lot of work to actually embed this in a coherent theory using the stochastic Koopman operator or using some uncertainty analysis that I'm going to show you. I was listening to several talks yesterday, and the methodologies that were being deployed, good methodologies, were on stationary data. Now, in many situations, you actually have non-stationary situations, non-stationary context. Take a look at COVID, right? Every now and then, it just exponentially takes off. So that's a non-stationary process, and I'm going to mention a little bit that this Koopman operator theory, actually in the stochastic context, is a non-stationary process theory for a class of processes. So even within the probabilistic context, it answers some questions. And then the last one that is particularly close to my heart is there is a long conundrum in dynamical systems, which is if you have two dynamical systems that you have exactly the same spectra, are they topologically conjugate? And von Neumann and then Sinai later solved this problem in the negative, saying that if you have a system with mixed spectrum or continuous spectrum for the operator, then the underlying dynamics might not be conjugate. And differences in the Lyapunov exponents. They looked at the shift on 2 symbols versus shift on 3 symbols. One of them has Lyapunov exponent log 2, the other one has log 3, but they have the same spectrum. They're not the same. They're not topologically conjugate, right? So the question that we do need to ask, because it is important for the very practical issues on comparing, for example, your model and the data that's out there. Are they really the same, or is this particular observation of the system the same as some other particular observation? That in dynamical systems is solved by conjugacies. The question is, can you always solve it by the spectra as well? And in the class of systems, we know the answer is yes, and I'll show you an example where we utilize this on algorithms. All right, this is a little bit more of intro. These are the kinds of things we'd like to do in learning of dynamical systems: provide a model, provide quantification of uncertainty, then provide a methodology for control, enable analysis, enable model reduction, enable prediction and causality analysis, and what-if analysis, and so on and so forth. All of this can be done in the context of the theory that I will describe. And so let's get into the bones of this, meat or bones, depending on how you look at it. So we are starting with some observables on the phase space F. Is there maybe a... Yeah. Do you know which one it is? Maybe not. All right, maybe not. So observables on the phase space F. I'm going to, well, the space of all the observables, all the functions on the state space is a space itself. It's a vector space. You add two of them, you get a third one. You don't necessarily need to specify the functional space to start with, right? In geometry, we specify pullback operators that are the same composition operators without ever specifying the space. But if you want to do something with the spectra, then you'll need to specify the space. But the Koopman operator is just this U or UT in the continuous time, U for the discrete time, where you compose the observable F with the map T. A little bit of history. Koopman observed this in Hamiltonian systems and transformations in Hilbert space in PNAS in 31. Carleman had a similar idea, and today we know this under Carleman linearization. I won't speak much about it, but it relied on embedding with, it's the same as Koopman's idea. It relied on embedding with monomials, polynomials in general. We tried it in practice because of the aspects of the polynomial explosions. It's difficult to make it work, and maybe that's why it wasn't used so much. Koopman von Neumann extended it in 32, said that systems with continuous spectrum for that operator, it's a linear operator, so you can talk about its eigenvalues, eigenfunctions, and so on, or maybe continuous spectra with generalized eigenfunctions. Observe that you can have systems that have deterministic dynamics but chaotic spectrum. This is really the prequel to chaos theory. They observed that you can have very, very complicated dynamics from a very simple, I think they took a two-dimensional map and showed that it has continuous spectrum. And then Moritz, Wanzig, a number of people work on these types of projections. That's all based on the associated Koopman operator. The difference is they're not presuming they have a closed invariant subspace, so the projection contains some kind of memory term and things. So that's a crash in where the kind of crash course in where the beginnings come from. In the vector fields case, if you have x dot is equal to f of x, and then you add maybe control, u is some control input with a of x in front of it, then the generator equation is going to be an advection equation without a minus sign, right? The adjoint of that would be Perron-Frobenius, and since that's linear, you can ask for eigenvalues lambda and eigenfunctions, and this might look more familiar. Here is a linear operator of differentiation on phi, so that's directional differentiation. F is my vector field. If that holds, then I have eigenfunctions. In the evolution case, it's this, ut phi is equal e to the lambda t phi. So lambda would be an eigenvalue. Again, that's a little bit of a misnomer, but that's from linear systems theory. E to the lambda t is really an eigenvalue of ut, but we call lambda an eigenvalue in the continuous time case. So you will see that systems with discrete spectra that have eigenfunctions have nice invariant subspaces, and those that don't. And that makes a big difference in whether the underlying object that you're dealing with is linear or nonlinear. But generally speaking, we can get geometry of level sets of Koopman eigenfunctions in state space from these eigenfunctions, and then projections on Koopman eigenfunctions that lead to something that is called Koopman modes. I'll speak about them a bit more. So here is a little proposition that tells you the following. You don't need to read it. If you find an eigenfunction and you find its level sets, that provides you with an invariant partition of the state space. So it's going to foliate the space into subsets that the dynamics maps into each other. Yeah. So the simplest invariant partition would be that the fixed one. So every set just gets mapped into itself. Take energy in the harmonic oscillator, every circle just stays invariant, right? It gives you, so these would be the eigenfunctions at eigenspace 1 of the discrete Koopman operator. You take their level sets, you get the geometry. In the dissipative case, you need to expand the concept of invariant partitions from ergodic theory a little bit to define what are called transient partitions, transient invariant partitions. In ergodic theory, we have only recurrent or quasi-recurrent partitions. But here is van der Pol oscillator, and in these terms, The invariant partition is really partitioned into these sets that are either circular sets that converge to the limit cycle that's here, or the sets of the phase that Winfrey defined as isochrones. So here is the point that I want to make here. Out of the different eigenvalues and associated eigenspaces, you can get objects like invariant sets, isochrones, and a new object that's called isostables. Isostables are the sets that are depicted here in white, and you should think about them as crunching towards the attractor as time goes to infinity, such that they observe the time and linear dynamics close to the attractor correctly. So if the concept of Lyapunov functions comes to mind, then yes, these are in some sense optimal Lyapunov functions. You're going towards the attractor in kind of uniform way, but you go from one set to another in an organized way, and you could say, well, I can always draw some circles, and I'm going to, if you just follow the dynamics. The key point is that they need to behave correctly close to the attractor, and that's what makes them unique. So this concept of isostables is today used quite a bit in control theory is related to that. But again, the point here is that if you have a discrete spectrum of that operator, if you have eigenvalues, if you find them and you find eigenfunctions, you will get objects that determine the geometry of the underlying nonlinear dynamical system. How do you compute in this case? I'll come to DMD very quickly, but how do you compute in this case? This is actually quite simple. You take the observable, any observable, this is a generic observable F, and you start from an initial condition. Here is the state space of the standard map with increasing quote unquote energy. And you're seeing the trajectories here, and you're seeing the level sets of a Koopman eigenfunction here. So if you just take an arbitrary function f and average it over trajectories and then plot that number as a color, you get these kinds of plots. In other words, that's data driven, right? The only thing that you really need is an observation. For example, you need a pressure probe inside a combustor. That's a real example. That's from a 2004 paper. And you will get the state space, some understanding of the state space, at least the invariant sets. So this is the time averages. You can extend the notion of time averages by multiplying. This is in continuous time case where I'm taking the composition. Note this is the Koopman operator here. Ut is a composition of f with st. When I'm multiplying with e to the minus lambda t. For lambda is equal to 0, I get time averages in continuous case. For lambda is equal to I omega, for omega being the eigenvalue on the limit cycle, I get isochrones. For lambda is equal some s, which is real, that's the decay exponent, the flow k exponent, you get isostables. So all the classical dynamical systems objects can actually be obtained directly from data using, let's say, these weighted averages, and are related to eigenspaces of the Koopman operator. All right, but let's ask for a little bit more. So hopefully I convinced you that from analyzing Koopman operator you get geometry. So let's go to the next step and use it as a modeling framework. So let's say that we have an absolutely abstract space P. There is no numbers associated with it, and we know that gets mapped to P prime somehow. It's abstract. And then we say, okay, we're going to put some states to it. So for example, in the Newtonian case, we're going to put x, the positions and momenta. So this x here consists of, let's say, positions and momenta in that case. But in general, it's some set of observations that I put together in a vector. So let's suppose that I put a basis f on that state space and expand the vector x using coefficients cj in a basis. And then I observe that that fj is an individual observable on the state space, and so the action of u on that basis function fj right at the top I can write a sum matrix djk fk. Yeah. So for every j and k, I have two basis functions. I can connect, just like in linear algebra, finite dimensional, I can connect these two by some matrix. So in the cases, you need to specify the functional space and all that. But in many cases, you can represent the Koopman operator as a matrix. Ask the opposite question. So we're starting from the dynamics over here and saying, okay, that maps to that over there abstractly. And so we can associate an operator that is represented by a matrix on it. And that's where most of the analysis today comes from. Find a finite section of that matrix, for example. It's a good idea. I'll describe that idea and describe where it also might fail. But in general, think the opposite way. If I have a bunch of observations, there is an evolution. If my evolution is Markovian, there is an evolution operator associated with it. Forget T, think U. And if you can find that U, you have a model. And the question becomes the opposite. It's not, I start with a vector field, as Koopman and von Neumann did. I exhibit a matrix, and then I find eigenfunctions and eigenvalues, which is very useful. The inverse question is really the identification question, isn't it? So you could ask the question, when can I represent an infinite evolution using a finite system of observations on some state space? And that's where I'm going to discuss this concept of representation. So this is to a certain extent a critical point what I'm going to say next, but before I do that, I need to introduce the idea of the spectrum. I've avoided the functional spaces so far. I'm going to introduce them now. There is always a way, well, for a very, very large class of dynamical systems, there is a way of constructing Hilbert spaces as a tensor product space of functions on a tractor, but defined on a whole state space, and the functions off a tractor. The functions on a tractor, think of a limit cycle in van der Pol. They are, let's say, sines and cosines of that theta observable on the limit cycle, yeah? Fair? But that can be defined in a whole state space. Yes? The observable theta, by a variety of people have proved these theorems, you can extend theta to the whole state space from the limit cycle. Yeah? And then you have functions defined on a whole state space. That's in HA. And then HB are functions that are zero on the attractor and, let's say, live in some subset of space of continuous functions off attractor. You can construct Hilbert spaces like this. If you're interested in digging a little bit deeper, there is a paper in Notices of the American Mathematical Society on the right, and Yanis has a question.
If there is one basis for the limit, like if there is another basis, the limit type is here, you can do the theta beyond the basis?
Yes, you can split, in that case, you can add the functional spaces. So if you have two basins, take all the functions, so take HA to be the sum of HA1 and HA2. Functions in HA1 have support, yeah, okay, you see. Okay, what is nice about this is that you can use and what is proven in an earlier paper of mine in 2019 or 2020, is that you can use a theorems like Barry-Simon's theorems to show that that U can really, the Koopman operator can really decompose over the projections that I could call on a tractor and off a tractor. That are the on a tractor one are associated with eigenvalues and the spectrum that is on a tractor and lives in some space like L2, for example, on a tractor. The off a tractor functions give you the decay like the Floquet exponents that I just mentioned, yeah? So there is a nice spectral theorem in these spaces, and you start understanding that you do have these anisotropic spaces, similar to what we have seen in chaotic dynamics in the past. You have to construct these anisotropic spaces, but in them, the spectrum is nice. And then ultimately you can get expressions like this, and I end up giving you some practical suggestions on what happens. G is my vector of observables. X lives in the state space like before. Z, you can think of as an indexing set. Let's say in a fluid flow, Z could be the 3 spatial coordinates, Z1, Z2, Z3. So G, that is a function of space and state space, so it's a function of space, you can expand into its time average that I already mentioned, a sum that depends on eigenvalues, lambda j's. This could be on the unit circle if we are in L2, but off the unit circle if we have spaces like HB. So for measure preserving systems, these lambda j's are going to be I omega j's, I being the square root of -1. And then you have this part that is the continuous spectrum. And so if you have something like Lorentz attractor that's going to feature prominently, and this is not going to feature prominently, this is just the time average. So if you're doing some physics, the idea that you're decomposing the time average out immediately is probably an intuitive and useful idea. For example, other decomposition methods like proper orthogonal decompositions actually don't have that feature. So people subtract the mean because that's intuitively a good thing. But the Koopman mode, and this is what was called in this 2005 paper, the Koopman mode decomposition. Phi j's are eigenfunctions, lambda j's are eigenvalues, and sj's, I call them shape modes, but we call them later Koopman modes. And then Peter Schmidt invented DMD in 2009, and then Clancy Rowley and myself and a few others connected DMD and KMD, this decomposition here that appeared in 2005. In particular, without this, we connected it to dynamic mode decomposition. So that's a brief history there.
May I ask a question?
Absolutely.
Yeah. The page before the K, how do you determine that K?
Let me see.
The sigma. Since you have a finite summation.
And I'm not determining it. It's a K. So if you have a linear system with linear observables, the K is going to be equal to the number of dimensions. But if you have a non-linear observational linear system, K is actually going to be infinite. Nice clarification though, yeah. So K can be finite or infinite depending on which functional space you are. Yes. Great question. Great question, and the answer is it could be in both, but in many systems that you see, it lives in the complex dynamics on attractor. And the reason it can be in both is something like x dot is equal to x squared, which is strange because it blows up, actually has continuous spectrum, and that's all in the dissipative part of the dynamics. But that's a little bit of an anomaly in a sense. There is a large class of systems for which spectra start from a unit circle in discrete time. The spectra are, on attractor are concentrated there. So if you have an on attractor L2, the spectrum is going to be on a unit circle. But then you have basically a copy of that spectrum for circle. So I think Ryan Moore and I call this a concentric spectrum. So there is depth here, and thanks for that question. But there is quite a bit more. If anybody's interested, please ask me after. Okay, so let me now go to representations, because I said I really want to turn the problem on its head and say I have a dynamical system. It's represented by some point M in an abstract set. And the only thing that I have accessible is some measurements that live in the set of functions little f. So in components, they're f1 to fn. Again, n in principle can be finite. If I'm really talking about measurements, that can only be finite and not infinite. So here is what a representation is. A finite dimensional representation happens if I find a set of functions little bold f such that there is a map, capital bold F, that has the property that when I apply it to little bold f, I get exactly the same action as the Koopman operator acting on f. So just for a moment, let me convince you that this is non-trivial. The left-hand side is action of an infinite dimensional operator on a finite number of functions. The right-hand side is a finite, possibly nonlinear capital F action on a finite number of functions. Right? So that's what I call the representation. We'll call it linear, provided capital F is a linear mapping. You've already seen one. If u phi is equal to lambda phi, then f of x is equal to lambda x is precisely that representation. Anytime I find an eigenfunction, I have a linear representation. Okay, that works. The concept is not vacuous. We'll call the representation faithful if any points m and n in the if the set of functions little f separates points in the state space. So no two points in the state space give you the same values of little f's. And the nice thing is that if we have two different faithful n-dimensional representation, I didn't say efficient. Efficient would also be that I cannot find any smaller representation. So let's say I could have x dot is equal to lambda x and x squared dot is equal to 2 lambda x squared. I could have those two and that would not be efficient because I can just take x dot is lambda x. Right? So if I have two of them and they're of the same dimension, then they're conjugate. They're actually conjugate. So that's nice. One example, which also is supposed to convince you that we should always start with spaces of complex functions and not real, is rotation of the torus. Imagine just very abstract rotation of the torus. Take e to the I omega 1, take rotation rates omega 1 and omega 2. Take functions z1 is e to the I theta 1 and z2 is e to the I theta 2. And then you get f prime is af for these two complex functions, where a is just multiplication, diagonal multiplication by e to the I omega 1 and e to the I omega 2. So if one has toroidal geometry, then complex functions come into the picture immediately. In general, if one has an arbitrary Koopman operator, complex eigenfunctions are there. So all the computations in principle should be in the complex spaces. This is my pet peeve with neural network approaches. Please, let's have frameworks in which are capable of dealing with complex functions right from the beginning and not do everything in real spaces, because for dynamical systems it's just not right. All right. Sorry about that. I thought I ordered this correctly, but so now let's talk briefly about the space of observables that are constant on joint level sets of f. So remember, the level sets of eigenfunctions give you invariant partitions. So let's consider all the functions that are constant on joint level sets of this set of functions f. And then we're going to say that the subspace of the space of observables is generated by a finite set of functions if it's the subspace that contains all the observables that depend on f. So let's say you have x as an observable, x squared, x cubed, x fourth, all of that would be in that space. And that's an infinite dimensional space. Now a finite dimensional, so now comes a set of results, right? So if you have a finite dimensional invariant subspace, that is equivalent to saying you have a linear representation. So you have a linear finite dimensional representations like that are associated with the spans of eigenfunctions and generalized eigenfunctions. So that's a nice characterization, right? So if you have eigenfunctions and general eigenfunctions, if you have a discrete spectrum, you will have linear representations. You have to find the eigenfunctions. I showed you already that you can find that from data by these weighted time averages, yeah? So it's possible to get them. If you can, that's it. Now, if you don't have eigenfunctions, like for example, for Lorentz, you have continuous spectrum, and you don't have eigenfunctions, there is still hope to find invariant subspace. Imagine that instead of x, y, and z, Lorentz gave us sine x and cosine y and some crazy set of 32 functions of x, y, and z. There is a finite nonlinear representation in that case. It is the Lorentz system. How do you find it? Well, you have to find the subset of functions that are closed. So this is the Eigen problem that I defined. It looks very much like this problem, which is the eigenvalue eigenfunction or Eigen problem in the linear case. But here we are finding the nonlinear representations. You can do it using neural networks. There are a number of attempts to do this kind of a thing where you represent the output. This is your point at time t+1. This is your point at time t. So you want to minimize the distance between next time point and the previous time point using this neural network for little f, this neural network for capital F, and this is your neural network for little f again, but at time n+1, and theta and psi are the arguments of the neural network. And so if you solve this problem, if you solve it to a certain precision, you know that to a certain precision you have a closed subspace. But remember, the characterization of that subspace is precisely related to the spectrum. If there, so it's going to have to be nonlinear if and only if there is continuous spectrum, right? So that's, I would say, a nice coupling between learning and understanding what kind of representations we can have if you tumble the problem on its head, which is forget about the system, the operator is your model. Now, can you reduce that model to something either linear or nonlinear to get benefit? All right, I won't spend too much time on this, but how do you get, yes, question, Yanis. So not necessarily chaotic. A pendulum, nonlinear pendulum has continuous spectrum, provably, and clearly you can only have a nonlinear representation of it. Among other things, I mean, the underlying cause might be different, but the system doesn't have to be chaotic in order for one to necessitate a nonlinear representation. So that's kind of interesting, right? If in pendulum, the best thing that one can do in some sense is action angle variables, right? But that's not a linear system. Although if omega of I is I, you would say, oh, that's a linear system. It's not, because of course theta is an angle. So if you wrote it properly with a with a complex function instead of theta, it would be nonlinear. All right. So let me briefly go through how. So I already kind of said it. So there are several different ways in getting the eigenfunctions, eigenvalues, and modes. This today we call spectral triple, right? Eigenvalues, eigenfunctions, modes. Then you can get these expansions and move forward. One of them is what I call the generalized Laplace analysis. You already saw the examples of it. You basically go through the spectrum kind of layer by layer. So at the unit circle, you start with time averages, then you subtract that out. Then you use whatever I omegas you have on the unit circle, use that in this sum. I know it looks complex, but when I describe it, I think it's a lot simpler. Use that in that sum, and then find the isochrones, various isochrones, generalized isochrones, and then subtract everything, all the components that are on the unit circle. Go to the next circle inside, and then multiply it with the appropriate lambdas, appropriate coefficients. So as you subtract the previous part of the dynamics that has kind of higher power, you actually get all the eigenfunctions and modes. So this fk is going to be an eigenfunction. If you actually take a projection on that, you get the Koopman mode. All right. So that's JLK, that you can get directly from data, and we use it in many, many papers. The other one that is quite satisfying because you get a matrix out of it, but it has some problems associated with it, is really what DMD, Peter Schmidt's DMD originally proposed, which is, hey, not in this sense, but it really is just this U tilde n is a finite section of the Koopman operator. Think of all the coefficients in that matrix that I gave you, slice off a part. That's a matrix, find its eigenvalues and eigenvectors, and you can find eigenfunctions and modes. Left and right eigenvectors will correspond to eigenfunctions and modes themselves. So they're dealing with the projection to the span of the first n basis functions. You can get nonlinear representations from a finite section. So let me describe this again. There is a matrix up there, and suppose that I have a finite set of functions, f1 to, so fj1 to fjn. And they depend on themselves and a bunch of other functions that are in the same basis. But all the other coefficients are 0. If you find that, you actually have a nonlinear representation. Think about x dot is equal to sine x. The only thing that you really need to know is you have x in your library and sine x, and they are linearly connected. X dot and sine x are linearly connected, right? So you can get, actually from finite section, you can get these nonlinear representations. So that's a little theorem that states that. That's in the AMS notices paper, I believe. All right, how do you get coefficients? You can also get coefficients from these ergodic averages, by the way. So that's interesting. So these f's are the basis functions, fj's. They're not orthogonal to each other. So the concept is find a set of functions, a library, fj, sines, cosines, polynomials, and then find the dual basis. So if they're not orthogonal, the dual is going to be different, and call those g's. And the only thing that you need to do in order to get UJKs, UKJs, which are approximate, that's a given, is the time average, limit when m goes to infinity, 1 over m, fj composed with t, so action of the Koopman operator on fj, multiplied with the complex conjugate of gk, the dual. So it's a simple way of, again, getting it from data, and again, it depends on ergodic. So you can prove that this exists from various ergodic theorems, and so everything is fine. Now, of course, this is easier to couch in the matrix sense. So these GKCs are obtained as this matrix F dagger F inverse F dagger. If anybody recognizes the Moore-Penrose? Yes.
And I guess the question is, do you actually need convergence of the operator, or do you have something much weaker to still be able to?
So that's a great question. And if you posit the problem the way I did, the only convergence that you need to think about is these time averages, right? So you don't need, in some sense, the early papers that I wrote, I always felt that exhibiting the operator is a little much. I mean, that's what we do most of the time today, but exhibiting of the operator is too much. If I can find its eigenfunctions, for example, I'm in a good shape. And so GLA doesn't depend on exhibiting the operator and convergence to the operator. It only depends on convergence of time averages, right? And the time averages are guaranteed on a very large class of attractors by some Birkhoff relative. I should point out that there seems to be a real misunderstanding in the part of the operator, theoretic analysis aspects of this, that you need to understand what the pointwise values on the attractor are. You don't. L2 is enough because Birkhoff tells you that for any function in a class, the time average is going to be the same, so you can happily compute the objects that you want, eigenfunctions, right? For almost every initial condition. That makes me happy. I'm perfectly fine with almost every initial condition. So we differ here from the machine learning community in general that necessitates the reproducing kernel Hilbert spaces, for example. In our case, we don't really need them for on-attractor dynamics, which is stationary dynamics, which is arguably the most relevant to at least us in dynamical systems. Transient dynamics in control theory is actually quite important. So thanks for that question. It actually enabled me to kind of make a remark on this issue.
5 minutes.
Oh yeah. Okay. Started a little late, so okay. All right. So so what is another way of embedding and getting good spaces of functions? And by the way, I'm not doing service here, very good service in describing all the work that has been done in understanding the numerical methods. And pardon me if now I don't mention something that anybody has done. It's by no means a put down or anything. But there is a lot of work that has been done on understanding of this. Matt Colebrook and Alex Townsend are in the back. They're doing some really fascinating stuff in this context using spectral approach, for example. There is a group up in Washington. I don't know if Nathan and Steve are here, but they have done work on this and done a book on it. So there is massive literature on this that I'm not doing service to, so forgive me for that. It's not an intent. I'm just trying to say a couple of messages in the context of what I believe is interesting and important for us collectively to understand. So one of the things that you can do is use tachyons. In the dynamical systems community, we grow up on understanding what the tachyons embedding theorem is, and indeed it creates observables from a single observable along the dynamics. That's something that's quite interesting, right? So f and f composed with t, of course, are different functions. They're not orthogonal. You might have problems with separating things, like if you're embedding using tachyon's theorem, you can get embedding a limit cycle, you can get something that looks very much like a line. So you have to be a little bit careful as to how to use them, but they're very interesting from a perspective that if you formulate the matrix U, based on them, you get a companion matrix that in the last column has these C1s to Cn's, and we have the property of the dynamics that this converges. So the nth iterate of f under the Koopman operator minus the span of the previous things that you have, if that goes to 0 when n goes to infinity, and that does for a large class of systems, but not for mixing systems. So mixing systems and chaotic systems are an exception. Then you will get to pseudo spectrum of the Koopman operator, which is a nice result. So you have a precise result that tells you that you're going to be computing something real. If you just take the x prime is 2x, so the doubling map, or z prime is z squared on the circle in complex notation, the finite section method actually fails. If you want to take a look at it, there is a paper on numerical approximations that I wrote. So one does have to be careful with finite sections, and some of the approaches, like what we have done with periodic approximations, in fact, remedy that. All right, so let me talk a little bit about robustness towards the end and the various applications that we've done. If you have that expansion on the top that now you've seen 10 times, you can ask, well, I have a residual, so let's suppose that I have a signal with a noise. How do I make sure that I'm not representing the noise using the modes? It's a good question. Fair. So you have a limit cycle, but it's perturbed by noise, and you're saying, well, I'm going to take 100 modes and everything's going to be fine. Well, you're overfitting in that case. So an important question is, how do you make sure? In Koopman context, you can do this. This is recent work with Ryan Moore and Maria Fonoborova. What you're seeing top to bottom, hopefully your eyes are seeing that as I go from 10 mode representation to 100 mode representation, there are these more Gaussian shaped residues, PMR. But also, if you saw the values, this is 10 to the minus 14. If you use 100 modes, on a system that you're observing with noise, of course, you're going to represent everything perfectly fine, but you have just represented a lot of noise. So the right place to be is somewhere here, around 50. And there is a criterion for that. This is a curve that shows you that you stay within the bounds. Green is the bounds of what the uncertainty was estimated to be. There is a criterion that shows you that you should be somewhere right here. If you represent with too many modes, the percentage of time you're staying with your signal within the green bounds actually goes down. So you're overfitting. So you have a pretty precise criterion and a nice algorithm. In this, it should show up on archive. There is a very natural way of doing control in this context, and that is expand the state space. Look, if you're connecting a control system to a dynamical system, that other thing is also a dynamical system. So take its own variables, u. I mean, that's a supernatural idea. And again, there was prior work in this, but I do believe this particular formulation happened first in my paper with Milan Korda. So you have your f, kappa plus is now the next time iterate, and you have a shift on the space of sequences. Now, shifts on space of sequences for us dynamical systems people, they are normal dynamical systems. There is nothing unusual to them. So you can get a Koopman operator on x and on u. And if you do that, then your approach to finding your matrix changes a little bit. In particular, if you just do a linear lifting, so you assume that linear lifting in control variables is enough, you get this nice system to minimize over A and B that is going to give you a linear control system in the embedded space. Now, that's not fully what you really need to do is take the tensor product of all the functions of x and u. That's the exact representation. And then you have bilinear systems that you have to deal with. But it's a useful thing to try and see what the leakage is, right? And so it leads to very simple control actions. So instead of this, let me mention two things and I'll finish. One of the things, and Will Redman is right in the back over there. He's not going to give a poster on that tonight, but he's done some really, really nice work with the rest of the crew here in understanding that a neural network itself can be, a stochastic gradient method on a neural network can be understood as a dynamical system. And I should mention that Yanis worked with us on this as well. So you can say, okay, why don't I prune based on Koopman modes? If I have the average mode being very, very small, maybe I should dismiss those nodes over here that have that average mode very small. That's the basic idea. We call it a mask, but you can do this with various Koopman modes. Here is what happens. The classical ways of pruning, so what you're seeing here is a compression. So how many nodes have actually been taken out of the picture. And what you're seeing here on top is that, for example, the magnitude type pruning in neural networks is precisely, at least that's what the numeric says, it's precisely the Koopman mode, average mode. Remember that average mode, the time average. It's pruning based on that. It also turns out that gradient pruning is the pruning based on the Floquet, well, not Floquet exponent, but conversion, the isostable exponent. So the methods that people found effective in pruning neural networks can actually be described theoretically in dynamical systems, theoretically nicely in the context of the Koopman operator. You can extend that and say, hey, okay, but how about, okay, so you showed that two types of pruning, two algorithms for pruning are the same. How about more generally, can you prove that you have two types of algorithm? People are asking, well, maybe it's the same algorithm. And if you have the same spectra, you can say, as I argued before, in the cases when you have discrete spectrum, you can actually say you're looking at the same dynamical system. So Will has done some additional work on that. The general question, as I pointed out at the beginning, is not fully answered. But if you're interested, look at this paper of Alan Avila and myself that defines extended Koopman operators. So there are operators on tangent spaces and in general in the RAM cohomology, right? So how does the dynamical system move functions? That's Koopman. How does the dynamical system move vectors? That is going to give you some Lyapunov exponents. How about forms, right? So the conjecture here is that if you prove that all these operators have the same spectrum, then two dynamical systems have the same spectrum. That's an old question. I'm not saying we proved it in that paper, but it is relatively close, I think. Here is Will's work, and you're seeing two algorithms that are known to have conjugacy, and you're seeing basically the same spectra. The dots here in the middle, algorithm 2, the ROM's algorithm 1. All right, so I'll entertain you with this for the end. How many of you play online games? Nobody, as if I guessed. Well, maybe a few people. I was just in Kansas City, and it was a conference actually on network security. And when I asked the same question, because we are applying some of these methodologies in network security, when I asked this question, many people raised their hand. That was interesting. But anyhow, so even the game has its operator. And so what we could do here is play, to either disbalance or balance this joint work with Joao Hispania and the crew at AIMDyn. You're seeing that there's the same minimization there, but here is the plot that I wanted to show you. On the horizontal is the prediction, and on the vertical is the real from the game, right? So we constructed a Koopman model by exhibiting that matrix. Yeah, that's what we did. So I don't want to, not necessarily to go through the details because I think I sort of told you what they are. So you would like this set of points to be exactly on the diagonal, and they're pretty darn close, right, between the prediction. Why are they not the same? Well, the game is, well, in some sense, stochastic, right? So the distribution that you have, in that case, the Koopman operator theory predicts, if you have a stochastic system, that you're going to be looking at the expectation. And I think that's born pretty well from this. So the point I want to convey is, even for these really strange game theoretic, discrete, stochastic systems, there is an operator, there is a model, and it does pretty well. And I'll finish with this. This is a soft robot from our lab. This is work with Elliot Hawks and his group. He's a soft roboticist at UC Santa Barbara, really a fantastic person in soft robotics. What we do is there's a soft arm. You're seeing these LEDs on the side, and we are perturbing it with noisy step inputs. And what it's basically doing, it's like the baby flailing its arms, trying to figure out what it can do. And then we'll give it a task. So it learns the Koopman operator for itself. And then we'll give it a task and ask it to follow, in this case, follow a stick. We also gave it the task to throw a ball and a bunch of other things. So there you go. There is a stick, and it's supposed to follow a stick after it has been learning. This was sped up, but it was 5 minutes of learning, and as you can see, it does pretty well. Right? These are horrible systems to model. I don't know if anybody has tried, but constitutive relationships for cloth are not very easy to come by. This is cloth with 3 pneumatic actuators on the inside. The point is, it has a Koopman model, it learns its own model very fast, obviously beats pretty much any, I'm gonna say this and then have somebody shoot me down, obviously beats any other approach in machine learning right now for dynamic behavior by poles. If you want the margins, it's I think 10 times faster and 10 times more agile than anything else out there. And the competitors are strong competitors that are using a variety of different methods. So with that, I hope I convinced you that this is worth looking into. I hope I convinced you that looking at the operator as the model is worth thinking about conceptually, that representations is a good conceptual kind of framework to to do model identification in, because the operator is infinite dimensional and the representations are finite dimensional. And then hopefully I gave you a range of different things that either we have done or the applications that are waiting to be opened up. So I want to thank DARPA especially. They've been sponsoring us for a good 20-something years. And then ONR, Reza Malek Madani, and FOSR, Fariba Farouk, who's also at DARPA for a while. So that's it. Thank you.
You are giving all possible actions with the pilot tree.
Yeah, it's.
And then after it, so it's running the Koopman for the system plus the station.
Yes.
And after you've done that, when you say do this stuff, this is then the population.
It's LQR on the task of tracking the stick. That's a great question. I didn't have time. So let me respond to a couple of things. The way you can view this flailing is basically a sampling that enables you to get the Koopman operator. Although the number of configurations that the system can go in is infinite dimensional, we are sampling it a little bit, as I said, just like a baby is waving its hands. Then on the question of control, we have an A matrix and a B matrix. We lift linearly, and we do LQR on it in the lifted space, not in the state space. The number of modes, we use delay coordinates that I have described, so Krylov. And then in order to reproduce, you need, I believe, 6 of them, 6 delays, besides all these LEDs that have XYZ. So the state space is, I don't know, the observable space is 100 dimensional or something like that. Now, so relatively small for this system. Now, when you include control, you only need 2 time delays. So you could ask a question, well, I'm not observing the whole arm, so don't I need more because time delays replace space observables, right? So don't I need more? It turns out that you need very few. And you could say, well, how is this connected to Newtonian dynamics? But feedback control reduces it to 2 time delays. So that's specifically what was done there.